All right, so we're looking at chapters 3 through 5A, I'll call it. That's up to and including just the force on a free particle, that F equals QVB. That also includes the right-hand rule, so I'll sort of go over that. But in chapter 3, we have the definition of current, and the definition of resistance, V over I. Now, you'll use Ohm's law, of course, in the circuit, so you're not going to see a separate Ohm's law problem, but you might see a problem that delves into this idea that the resistance is proportional to L over A. The resistivity times L over A. It might be one of these problems where, like we did in class, where I give you the dimensions, and then you have to calculate the resistivity and then determine it from a table, something along those lines. But it being able to calculate the resistance or the resistivity or the length or area from that. Chapter 3. I think it might have been all from chapter 3. Oh, and then also power. Power was V times I, V squared over R, I squared R. I mean, all these equations are on your equation sheet, so don't worry about memorizing them, but know how to calculate the power if I give you that. That might also come up in household circuits, because with household circuits, to calculate the total current, you have to know how to deal with the power. Then in chapter 4, we have combination circuits. All right, definitely going to have one of those. Multi-loop circuits. Definitely going to have one of those. Like, I've already written those 2 questions. You have a combination circuits. I think it had like 8 resistors in it in various series and parallel. But I set up the numbers so that they work out well. So keep that in mind as you're going through. Like, if you're really astute at it, you should just be able to look at it and tell me, without writing down anything, all the voltages and currents. But don't do that, because if you want full credit, then please write down your work, okay? Excuse me, if you just write down your work on your exam. All right, so the multi-loop circuits, that's where you have to solve the system of 3 equations. I've tried to make the circuit as simple as possible, but it does require you to substitute equations into one another. I know we worked some in class where that wasn't necessary if you chose the right loop, but in this case you will have to solve the system of equations. So make sure that you're up on that. It's not a difficult system of equations because I've just tried to make the numbers easy, but it is a system of equations with 3 unknowns and 3 equations nonetheless. All right. That was basically it, I think, in that chapter. I mean, we talked about electromotive force and the loop rule and the junction rule, but all that comes in with these different kinds of circuits. So from that chapter, oh no, I'm sorry, RC circuits are there too as well. So RC circuits, you need to be able to calculate the charge, current, voltage, and the time. For an RC circuit. You know, that largely means that you need to know how to deal with that exponential term. Remember, if you're solving for t, you have to take the natural log of that exponential term. If you're having difficulty with that, come see me today or tomorrow, and I can just help you. Once you see it, it's not that hard, but if you haven't done it in a long time, it might be hard. So make sure that you can solve the exponential using that natural log, the e to the x button on your calculator. Also be able to draw the plots on the free response, and there is an RC circuit that has a star by it. On the free response, I ask you to draw the plot for the charge, voltage, current, charge, voltage, or current for one of the charging or discharging, one of those. You know, the easy way, if you forget this, remember this. Our decay curve is e to the minus t over RC, and it looks like this, right? That's a decay. Our growth curve looks like this, and it's 1 minus e to the minus t over RC. And if you go to your equation sheet, you'll see that those functions are on the equation sheet, and they actually tell you, is it charging or discharging? I think that's right. Let's double check. No, I'm sorry, it doesn't actually. So you need to know, I'm sorry, it doesn't. Rewind, take that back. But you do need to know these two functions, which of these are for charging or discharging. We went over these in the notes. But this one is really just for the charge of a charging capacitor. Because the charge increases. That's really the only thing that grows in a capacitor circuit. This is for the current, voltage. Now, let me make sure I'm telling you this right. Yeah, so this is for the charge. That's not letting me write. This is for the charge of a charging capacitor. This is for the charge of a discharging capacitor. And then also the current and the voltage for a charging or a discharging capacitor also look like this. All right, so know your growth and decay curves. I'll ask you for the charge or the current or the voltage on that capacitor at any given time. I'll also ask you to characterize it based on the time constant. Remember, the time constant is this RC value. We use this in exponential functions a lot just to characterize the time. And remember, in order to completely charge or discharge a capacitor, we take 10 times this amount. So likely I'll ask you the question, how long to charge or discharge this capacitor? And so you'll calculate tau, and then you'll multiply that value times 10. I might also ask you to indicate tau on a graph. So, for example, if we're looking at one of these exponential functions, my value for tau would be like right there. It's not fully charged or discharged. In fact, it's only 1/10 of our fully charged or discharged. And in fact, down here would be 10 tau. So I might ask you to sketch that out. And then also don't forget that here, this approaches some maximum value, which is Q, is equal to CV. That is if I'm looking at Q versus T. So know those functions and how to characterize them and how to sketch them out. You need to know household circuits. You need to know GFI, circuit breakers, and you need to know grounding. For each of those, you need to know what they do, what they protect people against, and then how they work. And I'll ask you to write a few sentences describing that. You need to know what they do, how they operate, and what they protect you against. And what I said. So, like for example, the GFI turns off if the ingoing current exceeds the outgoing current. And it operates, it has a little ammeter, it just compares those two values constantly. And it protects us against getting shocked when we're in areas like that are prone to wetness. The circuit breaker. The circuit breaker protects our electrical system against overheating, like you get too much current going through it. What it does is it turns off if the current exceeds a certain amount, and it just has a switch that turns off when it does that. And then the grounding provides an alternate ground to the outside. It protects us when we have faulty devices by providing an alternate path for that electricity to flow, not through us, but out of our house and into the ground. So be able to describe for each of those in your own words and in a couple of sentences how they work. You might have some multiple choice questions too, just about the nature of your household circuit. It's laid out in parallel. All the devices operate at the same voltage. If you turn off one device, it doesn't affect the others. That's because it's in parallel. Okay? So those are household circuits, and I think that's the end of chapter 4. Yeah, and then in chapter 5, what you're going to see, you're going to have a cross product. I'm going to give you a charge. I'll give you a velocity vector in vector notation and IJK notation, and then I'll give you the magnetic field in IJK notation. So it'll be something like, 1I plus 3J meters per second, and, 2J minus 4K Tesla. and I'll ask you to find what is the force that's acting on, say, a 3 coulomb charge, and you'll just do the cross product. I just want to know that you can do the cross product, basically. We're going to see this more in the next test, and we'll sort of explore it a little bit more. But I just want to make sure that you can do the cross product and calculate the force that's on a charge. It's only worth like 7 or 8 points, but I just want to make sure that you can do it, and it'll definitely be on the test. I've already told you then, this is 7 to 8 points. I forget what it was. This is 15 points. This is 15 points. I think this was like 10 points. So I've already told you a good portion of the exam. Make sure that you can do all those individual things, all those different circuits. Make sure that you can answer those. Okay, I don't want you to be surprised by them. You're going to see a multi-loop circuit. You're going to see a combination circuit. You're going to see an RC circuit. And you're going to see a cross product. That's most of the free response. And then I'll sort of fill in some space with a couple of smaller problems. Okay? If y'all took it right now, how would you feel? What? What did you say? 60? No, you could do much better than 60%. Yeah, if I'm printing it out right now. 82. All right. Let's see. Also, probably on the free response, and then maybe also in the multiple choice, you're going to have some right-hand rule. Kind of like the ones that we had in the homework, the first few in the homework, where, you know, you have a positive particle traveling with this speed and, say, a magnetic field like that, and I ask you, what is the direction of the force? Or maybe I'll give you a particle that looks like this, and this is the velocity with a positive particle, and I ask you, what is the direction of the magnetic field? So be able to show the direction of the force, but then also be able to work backwards and figure out the direction of the magnetic field or the direction of the velocity. Remember, that's using our right-hand rule. We have our velocity, our magnetic field is our middle finger, and our force is our thumb. And it's really just a matter of getting them all lined up. So for example here, my force is up, my velocity is in that direction initially, so the magnetic field would be into the page in order to provide an upward force. And here, well, it's exactly the same. This one would feel a force that's going up. Velocity's in that direction, magnetic field into the page, force is up. Probably a free response with 3 or 4 of those, kind of like what we had in the homework, and they'll each count, you know, a couple of points. Okay? You have enough for everybody? Do you seriously?
The number of people who showed up today, I think so.
This is most of us. We aren't missing that many.
Emma means everything to me.
Oh,
She's not here.
she counts for more people than the rest of us. But, all right. Any questions, y'all? Any areas of weakness that you want to look at in particular? Your combination, your RCs, your multi-loops?
Can we do an RC circuit?
Mm-hmm. Let's see. Let's look back at an old test, if that's okay. This is spring 16, exam 3. Most of these are going to be like the ones that you'll see. Of course, they'll be different, but they'll be similar. Oh, this should be in the back of your book, actually. Yes, I mean, this looks like a lot like the exam that I just explained to you, with a couple of, you know, things sort of that could change. All right, so here we have a charging capacitor, as it says that the capacitor initially has no charge, and then it's connected to the battery and the resistor. So my circuit's going to look like this. I'll have a battery with a resistor and a capacitor. You don't have to draw it, but I'm just drawing it, with 2 mega ohms and 5 microfarads. And now the first question is just what is the time constant? Well, the time constant, tau, is equal to R times C. And usually I'm going to give you mega and micro because those are pretty common in RC circuits and it just makes the math easier. So I have 2 mega ohms, that's 2 million ohms, and then 5 millionths of a farad, that's 5 times 10 to the minus 6. So that just works out to be 10 seconds. And then I want to know what is the current after 5 seconds. Well, the current, now this isn't on your equation sheet, but you need to know that the current is a decay function. So if I were to plot current versus time, it decreases with time. Initially it's really big. While those charges are rushing on to that vacant capacitor, they rush right at first and then they sort of tail off. And so my current versus time of a charging capacitor looks sort of like this. It's going to be equal to I naught, that's my initial really big current, times e to the minus t over RC. My function is always either going to be a decay or a growth function. In this case, it's a decay function. My I naught is going to be V over R, that's from Ohm's law, e to the minus t over RC. And so that's going to be V is 10 over 2 times 10 to the 6th ohms times e to the minus 5 seconds, that's the time, divided by 10 seconds. That's the time constant. Make sure that you can solve these. This isn't the EE button on your calculator. It's usually called e to the x. Often it's second natural log. So I have 10 or 5 times 10 to the minus 6. That's my coefficient. And e to the minus 2. I get 6.8 times 10 to the minus 7. And that's in amps. So that's my current after 5 seconds. And then I want to know how long does it take to fully charge the capacitor? Well, y'all can probably tell me that right off because we already have our time constant. A was 10 seconds. So this is going to be 10 times tau, or 100 seconds. D is what is the charge after 100 seconds. Now, with the charge of a charging capacitor, the charge is increasing. So that's going to be a growth function. It looks like this, Q versus T. And that's given by this equation, which is on your equation sheet. All right, and so that's going to be equal to C times V. That's my maximum charge when the capacitor is fully charged. That's the charge that it has. 1 minus e to the minus t over RC. C times V is 5 times 10. That's 50 microcoulombs times 1 minus e to the minus... Oh, you know what? I don't even have to do this, right? Because at 100 seconds, I know that it's fully charged, that my growth function goes to 1, and so I imagine that this thing is just fully charged. Well, let me just sort of finish writing it. But I have 1 minus e to the minus 100 over 10. 100 is the time that I asked right here, and then divided by 10 is the time constant. But if you do this in your calculator, you'll find that this term is basically equal to 0. It's e to a really big number, e to the minus 10, so it's basically 0. So my answer is going to be just 50 microcoulombs. And if you just said that right out, that would be okay. You wouldn't have to go through this. And then sketch a plot of charge versus time for the charging capacitor. I could also ask you to tell me what time is it at a particular charge. So let's say I asked you, I wanted to know when does it have Q equal to 20 microcoulombs. Well, I would work that in reverse. See, I'm going to erase this left-hand side. When is Q equal to 20 microcoulombs? Well, I would say 20 microcoulombs is equal to C times V, that's 50 microcoulombs, times 1 minus e to the minus t over 10. because 10 is my time constant. And then I would solve that for t. It's a little bit hairy if you're not real familiar with exponentials, but it's a useful skill. I get 0.4 minus 1 equals negative e to the minus t over 10. So that's 0.6 equals e to the minus t over 10. And then I take the natural log of both sides. The natural log of 0.6 is negative 0.51. And this becomes negative t over 10. So you see the natural log gets rid of this exponential term. It's sort of like canceling it out. And so when I do that, when I take the natural log right here, it just leaves me with the exponent minus t over 10. And then I can solve that. It's going to be t is 5.1. So at 5.1 seconds is when it has a charge of 20 microcoulombs. That's a good indicator of the type of problem that you have. Now I could change it a little. Like I could say, instead of this one was charging, I could have it discharging too. In discharging, everything follows a decay curve. Nothing follows a growth curve. Everything's the e to the minus t over RC. The charge, the voltage, and the current. All right? I want you to be able to sketch the flux, be able to calculate the charges and the times, and know what the time constant means. It's a good question. All right? What else? Sure. Yeah. So, like, well, in this case, the current after 5 seconds, that's a decay curve. Let me I'll make a little table for you, so you can keep it all straight in your head. Charging, discharging. Charge, current, voltage. So for a charging capacitor, this looks like this. That's the 1 minus e to the minus t over RC. Everything else is a decay curve. So current looks like this. Voltage, oh wait, no, the voltage, so the voltage is actually a growth curve too. I'm sorry, I misled y'all. Voltage is a growth curve. For the discharging, Q looks like this. I looks like this. And V, yeah, it looks like that. And whenever you have these decay curves, like for example up here, it's going to be Q equals big Q times e to the minus t over RC. Likewise, I is I naught e to the minus t over RC. And then V is V naught times e to the minus t over RC. All right. Here, I naught, that's sort of like your maximum current. It's equal to V over R. Here, Q is equal to your maximum charge. It's equal to C times V. And here, this is like just the voltage of your battery. Although for a discharging capacitor, you don't have a battery, but you had to have charged up the capacitor at some point with a battery, and it would be the voltage of that battery. All right. So I know there's a little bit of memorization here, but you don't really need to memorize the formulae. You just need to memorize, is it a growth, or excuse me, a decay, or is it a growth function? And let me write this in its entirety. I have Q equals big Q times that whole thing, and here Q is equal to C times V. I looks the same here. I naught e to the minus t over RC, and here V is V naught. It's a growth, so it's 1 minus e to the minus t over RC. You're probably never going to see capacitors again, except for in the next exam, but you certainly will see exponential functions again. I want you to understand those, how they work mechanically, mathematically. Okay? Actually, I think you chemists will see capacitors again. I think in instrumental, I think Dr. Wayman's doing like circuits, so you'll see a little more circuits, but he does like op amps and stuff. You'll like it. It's pretty cool. I mean, not that capacitors aren't cool, or resistors, but they're just a little more practical, like for building instruments and the like. They can do more complicated things. Alrighty? Nicole, did that answer your question? Did that help a little bit?
Yeah.
Or did it muddy the water more? Alright. What else? Are y'all okay on your multi-loop and your combination circuits? Practice the ones that we've done. They'll be like those, but different, but similar. Make sure you know your household circuits. Make sure you know your right-hand rule. Y'all okay on the right-hand rule? There's different for that one application, the force equals QVB. Anything else? I got up early to be here. You could use the time. I got up at 1. Can you believe I got up at 1 o'clock this morning? I don't know. I sort of got bored. Go ahead, Kyle. 14 on this test? The one in the back of your book? Okay, so you know what? Good indicator, although yours will be a little more complicated, I think, in that yours would have a resistor down here. Like it would have a resistor and maybe not this right here. All right, do you want to do it like that? Just so you see it, it's a little bit different. It works out a little bit different. So I'll change it just a little bit, and we'll just make this, say, 1 ohm. All right, so the first job that you need to do is pick directions for the currents. So I1 is to the left, say, I2 is to the right, and I3 is to the right. No reason I picked those, it just sort of felt right for me at the time, but I wasn't basing it on any numbers. And then I want to write some equations. I know that I'm going to have 3 equations and 3 unknowns, so it doesn't matter which equations I write. I pick 2 loops, and I pick a junction rule. So I'm just going to pick a loop. I'll pick this one and go in this direction. And so that's going to be 5 minus 6I2. Coming up, plus 3 minus 2I1 equals 0. That's the top loop. Now let's pick the bottom loop, but you could do the big loop too. It doesn't really matter. But I'll start here and go in this direction. So it initially looks the same, but then I go down, and it's going to be plus 1I3. Being very careful that you get your signs correct here. And remember, I did 1I3 because I was coming down in this direction, opposing the direction of the current. And so when I oppose the direction of the current, I have a positive change in potential across resistors. I like to remember that, that's not what resistors usually do, but you don't usually go against the current either. So that's why you get that funky thing. And then apply the junction rule. Pick any junction, doesn't matter which one, and do the incoming currents. And for this one, it's I2 and I3. And then that's equal to I1. All right? So a good way to approach this would be to solve this one for I1, this one for I3, and then plug those into this one to get an equation that's all in terms of I2. So I'll solve this one for I3. I3 equals 6I2 minus 5. I'll solve this one up here for I1. Just to make the math a little easier, y'all, I'm going to make this a 1 ohm resistor. That way I just have 1 ohm right here. And then I1 is just 6I2 minus 8. I'll try to make the math as easy as possible, okay? Because you do have to solve these systems of equations. I'll try to eliminate all fractions so that you just get nice, easy whole numbers. But it depends on how you solve it. You might actually get some fractions or decimal numbers. So don't freak out if that happens, but I'll try to make it as easy as possible. Now I plug these in. I get I2 plus I3, which is 6I2 minus 5. Equals I1, which is 6I2 minus 8. Looks like I get some cancellations here. This cancels with that, and I get I2 equals negative 3 amps. So I2 then is 3 amps. I chose it to the right. That means it has to be to the left because it came out negative. Then I can just take that negative 3 and put it in here. I get 6 times negative 3. Notice I'm keeping my negative value until the very, very end. Minus 8. That's negative 18. Minus 8. Negative 26 is I1, so it's 26 amps. And I1 I chose to the left, so that means it's to the right because it comes out negative. And then I do the same right here. 6 times negative 3. Minus 5, that's negative 18, minus 5, negative 23. So I get 23 amps. I chose I3 to the right, so that means it's to the left. Goodness, I didn't get any of the directions right. But it doesn't matter. I didn't intend to. I just chose them randomly. You will have a question like that. It'll be, I mean, basically identical to that, except different numbers and maybe a different number of resistors, but very, very similar to that. You will have to solve a system of equations in that way. All right? Good question. You'll see it, so it's good to see it again before you sort of start studying. I know you've been studying for weeks now, but as you begin this final ramp up to the exam on Friday. All right. Anything else, Joe? Okay, with combination circuits, good with that? With household circuits business, answering those questions. RC, right-hand rule, cross products. Depending how you are on circuits, I mean, there's 30 points in circuits on this test. Depending how you are on circuits, actually more than that if you include the RC, but 30 points in the combo and the multi-loop. If you're really good at that, then it's not a real difficult exam, but I mean, most of us aren't real good at it, so we need a little prep to go into it. And I'm pretty good at it, actually. I like to think I'm not as good in some things, but I've done it for a lot longer. All right, y'all. What else? Anything else? No? All right. Well, we'll call that a quits then, but I'll be around if you have some questions now or later this morning. 7:15.